Good afternoon, everyone, and welcome to the Sturm, Liouville theory and sound wave representation. Our presenter today is Bill Gustafson from Colorado Mesa University. If you have any questions for the presenter during the session, please feel free to enter those into the chat at the bottom of the Zoom room screen, and we will address them at the end of the talk. So on that note, I'll go ahead and hand it over to you, Phil.
All right, thanks, Sydney. Thank you also to everyone at Hawks and for doing the online hosting for this conference, and for everyone at Metro State for organizing the conference. I definitely appreciate having this virtual environment because it here in Grand Junction on the other side of the mountains, just a lot easier to participate, especially if there's weather coming through. All right, so today I'm talking about bringing Sturm Liouville theory alive for students using voice wave applications. And so I like to try to blend together theory and application whenever I can with some sensory experience. In this case, listening to the results of the mathematics, and in this case, some numerical programming as well. All the results presented here are obtained from programs that I've written using some very simple naive programming style in R and Octave. I'm trying to get to the next slide. There we go. Sturm-Liouville problems are often first encountered in a junior level applied analysis course. And Sturm-Liouville problems are comprised of a specific type of second order ODE that you can see here. They're typically coupled with some boundary conditions of different types. And the coefficients, the P, the Q, and the W are generally pertinent to modeling particular physical applications. If you rearrange that first line of that differential equation, you can re-express it as a linear operator problem, an eigenvalue problem for a linear operator, where so we bring lambda y to the right side and divide through by negative w and so forth. And so L would be everything on the left. It's important for me to point out too that the w is known as a weight function that we'll need for an associated linear inner product. All right, so once you view the differential equation as an eigenvalue problem, you can use some powerful results from linear operator theory or Hilbert space theory, Sturm-Liouville theory. And so that's where we go to next. Let's see. First, an example would be a vibrating string problem. And so the Sturm-Liouville problem here is this undamped vibrating string differential equation with clamped endpoints. If you rewrite it as in linear operator form, your L is just going to be simply negative y double prime, and your weight function will be 1. And using basic solution methods for like a first course in ordinary differential equations, your solutions will be sines and cosines, but the cosines will go away when you use the boundary conditions to solve. And so you end up with just sines. And so your eigenvalues here can be m squared, and your eigenfunctions will be sine of mx. And so there's infinitely many of these for this string problem. All right. Other examples include Bessel. There's Bessel equations and Chebyshev and Legendre equations, Fourier, and so forth. And so these, depending on which operator you're looking at, these all form orthonormal eigenfunctions relative to the respective L, and they are complete in associated function spaces. This is a common setup for Hilbert space applications. All right, so to bring these ideas alive and see how they all work, that's what I want to do in this talk. I like using voice wave representations because it's a fairly direct way, an immediate way to bring the ideas to the students. They can record their voice and they can get to work on applying the ideas. All right, so this talk actually expands on a project that I did with one of my students last fall, Kyle Preistup, and as well as some extensions of that. So just somewhat informally, I'll define my space to be just common voice waves. And you can think of these as L2 functions on a time interval. There will be an inner product and a metric associated with the space derived from the weight function and the operator L. And so you can see here what that inner product would look like. And according to Sturm and Liouville theory, these eigenfunctions are complete in S. And you can, so therefore you can express, say, a voice wave as an expansion in terms of these eigenfunctions. Your coefficients have the form there at the bottom of the slide. They're sometimes called generalized Fourier coefficients, Gram-Schmidt coefficients. They come by different names, and with an orthogonal expansion, the derivation of those formulas are pretty standard for CM. So for the vibrating string, we had those sine waves, sine mx over the interval 0 pi. And so what you see here is just a graph of some of those eigenfunctions using R. All right, so those would be basically your basis functions for representing a sound wave. Before we jump into sound waves, I thought I'd look first at a simpler type of function, a discontinuous one, a square wave function that you can see at the bottom left of this slide. And I'll use 16 of the sine wave eigenfunctions. And I'll be computing using integrals, actually quadrature rules in R in this case, to compute the coefficient Cm and adding them together with the sine waves. You'll get the red curve here on the left that'll approximate the square wave in blue. And so that's gives you a picture for a simpler function of how a function from your space can be represented in terms of these eigenfunctions. On the right at the bottom is called a stem plot of the values of the absolute values of your coefficients. And so there's 16 of them. Half of them are 0, and the other half have certain values that are represented as heights of these stems. So C0 would be 0, C1 would be given by the height and absolute value of the stem, and so on. From Wikipedia, there's sort of a nice image that goes along with this picture. If you view the eigenfunction expansion as this red graph on the left, you can see a similar thing in the picture from Wikipedia. And so that's called a time domain graph, the red squiggles. It's your representation of your function over the time interval. And then the coefficients represented by these stems can be viewed as from this other direction as the amplitude of your the sine wave of each of the frequencies, frequency 1, frequency 2, frequency 3. And so the coefficients play that role in how much of each sine wave is required. They'll for the sine waves, you can also position the stems at the values of m along the x-axis so that they correspond or can be made to correspond to the frequency of each sine wave. So you know from the height of that stem how much the dominant frequencies based on the presence of those sine waves in putting together your function f of t. A couple other examples I want to look at. The Bessel equation of order 0 is here, and similar to describing a vibrating string, this one describes a vibrating circular drum head that's clamped around the boundary. This will describe the spatial distribution for a separable wave equation model for this. And once again, we can re-express it in operator form. And the eigenfunctions, when solving, will be, for the one I'm looking at here, would be a Bessel function of order 0, based on some choices I made for the original ODE at the top. This one's an order 0 one. The ZM that you see here are the zeros of the Bessel function of order 0, and so that's what the ZMs are. And so the form of this solution is analogous to what we needed for the boundary conditions and the sine waves. And so I won't say much more about that, but it's a solution process that my students would go through. The graphs of the Bessel functions are shown here using R to graph them. And one thing interesting to note is that the Bessel function of order 0 resembles a cosine wave that has sort of a diminishing amplitude as we go. So what we're looking at here is J0 of A1 being graphed in orange, J0 of A2 being graphed in green, and so forth. And again, this is comparable to the sine wave graphs of increasing frequencies on the previous example. The Bessel functions are often used to model human voice waves, because if you think of the vibrating drum had a circular geometry, you can sort of extend that maybe to our larynx and the vibrations of our vocal cords. I think there's more to it than that, but sometimes the argument is made to use Bessel functions instead of sine waves. Also, the decaying amplitude sort of reflects the loss of energy when modeling a voice wave over time. So there can be different reasons for choosing different eigenfunctions to represent your sound waves. In the square wave case, again, the Bessel function expansion in red looks similar to the sine wave expansion in the previous example. The stem plots of the coefficients do look a little different than what we had for the sine waves. But there's things to talk about there with my students. Another common Sturm Liouville problem in a class of this type, a course of this type, would be a Chebyshev equation, which you see here. And the solutions to the ODE, or the eigenvalue problem, are the classic Chebyshev polynomials. One of the advantages of using Chebyshev polynomials in representing functions is that they'll provide an optimal uniform approximation if your function space is comprised of continuous functions on an interval. In particular, then the sort of the home interval for Chebyshev polynomials are -1 to 1. And so the first several of the Chebyshev polynomials are graphed on this slide. All right. And so with the square wave example being sort of our benchmark here, you can see how the Chebyshev polynomials would do in representing that square wave. Okay, so for voice waves, let's see here. Let me see if I can play the voice wave that I'm using here. And if someone wouldn't mind unmuting themselves to let me know if they can hear this. Let's see, this is a recording of me. Let's see what it sounds like. Sound wave expansions. Yeah,
Yes.
Can you hear that? Oh, good.
Yep, we can hear it.
Awesome. All right, so on the top row here is the raw data for that sound recording, and that's in blue in the top row. And then on the right side of the top row is just a zoomed in version of that, just sort of a random portion in here somewhere. I just zoomed in on it so I can see what it looked like. And then on the bottom row in red is in this case, a Fourier expansion. And the vibrating string used sine waves for the eigenfunctions. And in general, we'll use both sines and cosines in a Fourier expansion. And so this will be a Fourier expansion using sines and cosines of the original sine wave, a sound wave. Only about 1,000 terms are being used in that partial sum the infinite expansion. And so you don't capture just based on a choice I made for what to plug into the computer. And so I just chose 1,000. And so some of the higher frequencies beyond that are not incorporated into this red wave, so I don't get the full blue one. I think the human ear can hear up to 20,000. So going out to 1,000 captures some of the dominant lower frequencies, but it doesn't capture all of them. All right, so, and I just want to remind you again, what we're seeing here, the red curve on the top is the representation, not of the square wave in this case, but of your original voice wave. And then the blue, what I'm calling a frequency domain graph, corresponds to the coefficient information that's used to construct the voice wave. All right, so what you heard when I played it was me playing this Audacity sound wave that was, I used, it was Octave in this case. I used Octave's wave write command to take the vector representation of the Fourier expansion and write it to a wave file that can then be played. All right, okay, so this is the original, and then this was the Fourier representation. So let me play for you the Fourier representation. It won't be quite as clear as the original because I'm missing information because I didn't do a full expansion. So here's what it sounds like. Was that loud enough? Did anyone hear that?
Yes, we were able to hear that.
All right, the original is much louder.
Sound wave expansions.
And then the Fourier representation, a little bit more muffled. Okay, so that's just hearing the results of that expansion, hearing and seeing the results of the expansion. For the Bessel expansion, I'll take that same voice wave recording of me and in Octave, I'll compute the coefficients and the Bessel functions and I'll add them up. In this case, I think I'm only using out to 500, sort of quasi-frequency terms, only 500 terms in the expansion. And so you'll get the red wave on the bottom, which is missing some high frequency information. So it doesn't capture the entire blue wave of the original. And then the so-called frequency domain graph on the right, again, is just the sort of the analog, it's the coefficients that go onto each of your waves so that when they add together, you get the red one. All right, let's hear what that one sounds like. You'll have to listen or turn your volume up a little bit more because this one's going to be more muffled than the other ones. So it's just kind of fun to hear the results of doing this. And so again, using about out to roughly a frequency of 400 or 500, this is what it sounds like. I can't make it any louder than that. I tried, but that's all I'm getting. Right, so anyone want to hear that again with their volume turned up? All right, well, when my students do this, they'll have the computer in front of them and they'll be able to hear and play around with some things. So the Chebyshev case I'm still working on, so I'm not ready to I don't have anything to share there yet. It's a little bit more complicated, sort of transitioning off the interval -1 to 1 to a more general interval for your voice wave. And so there's more to do there. Okay, so in conclusion, the idea here was to take some really important theory from applied analysis and just see how it works, how it gets applied to voice wave representations. And I think it's kind of fun to blend together these different components, the theory, the application, and the numerical programming and some sensory component to that as well. From here, there's more things students can work on. You can explore sort of frequency filtering applications in the coefficient domain over here. You can zero out certain coefficients. You can try to denoise your signal by zeroing out small coefficients in this blue graph, and then reconstructing an approximation to your original sound wave and seeing how that sounds. And so some of the projects in some of the courses I teach pick up where this leaves off. And in that case, it's usually with Fourier representations because the FFT command is in most programming languages. And so, and the inverse FFT as well. And it just makes the topics easier to access. Whereas Bessel functions and Chebyshev, you tend to have to kind of write your own programs for those applications. All right, that's the end of my talk, and so I appreciate everyone being here. And if you have any questions, let me know.
Well, thank you so much, Phil. It looks like we do have about 4 minutes left. And so if anyone does have questions for Phil, please feel free to unmute yourself or put those in the chat as well. And I believe he'll be happy to answer them. And if we do not have any questions, that is okay as well. As a reminder, I'll be posting all of the links to the next session in the chat. So you can click there in order to go to the next session, or you can always refer back to the conference website. And then as a reminder, always feel free to jump into the Hawks virtual booth as well to connect with a member of our team and also be entered in to win that $50 Amazon gift card. So thank you again so much, Phil, for all the valuable information you shared with us today. And if anyone has any remaining questions, feel free to unmute yourself or chat in if you'd like.
I'd like to ask a quick question.
Yeah.
Can you discuss a little more the scope of the class that you do this in?
I'm sort of morphing together a couple of different student experiences. When I developed a class, started off as a topics class, and now it's just a regular elective in our math majors. It's just called Fourier Analysis, and I'll focus on the Fourier case, and so that'll be a semester-long 3-credit class where they do a lot of this stuff, and then the Fourier Bessel piece, along with the Fourier sine piece of this presentation, came out of a project, a senior research project with one of our students last fall. It was a 3-week project. It wasn't an extensive long project, but he looked into the Bessel case. And so we looked at some papers involving Bessel expansions. And then finally, the other piece to this is that our applied students will take a semester of applied analysis, where they first learn about the analytical side of things for PDEs and separable PDEs and special functions and things like that, including method for Frobenius to find Bessel function solutions to the ODE. So there's a couple different course experiences that if my students here at CMU are in the applied concentration, by the time they're a senior, they can, as a capstone experience, they can pull these all together. But the class where I get the most opportunity to do a lot of this stuff in is just a Fourier analysis class. That's one of our electives.
Thank you.
Okay, you're welcome.